Hello, everyone. Welcome to our second session in the various sessions that we're presenting at the UAVSI conference this week. This particular session is titled Applanix UAV Products and Services, Meet the Experts, and we do have some experts with us today. I'd like to introduce Joe Hutton, who's our Director of Inertial Technologies and Airborne Products. Joe's been with the company for, well, forever. I mean, right from pretty much the beginning. He was one of the first employees with the company, so a wealth of knowledge there. And Srdjan Sobol is our Airborne product manager, and he's involved with a lot of our integrations and working with our technology on a day-to-day basis, has a wealth of knowledge when it comes to implementing solutions to turn your UAV into professional mapping solution. So I've got two experts on hand with us, and we certainly appreciate them taking the time out to spend an hour with us to answer any questions you may have. My name is Brad Schmidt. I'm the Global UAV Sales Director, or Sales Manager, I should say, and what I'm going to do is moderate this session for you today. So you can ask questions. This is a free form session, so any kind of UAV questions you may have, please feel free to ask. Now, we did have our first session this morning, which was basically what is direct georeferencing and why use it for a UAV survey and mapping. So we kind of went through what that is and what the technology offers. So we wanted to kind of use that session to leverage questions. But if you're just joining this session for the first time, no problem. Any kind of questions you may have, please feel free to ask. Now, I do want to stress that our area of expertise is really in integrated GNSS INS systems, and basically taking a standard UAV and what it takes to turn that into a professional mapping system. So that's really where our expertise comes into play. So if you kind of direct your questions more in that area, we'd be able to be very flexible in terms of answering those questions for you. So as we go through, as I say, there's a questions box here. Please feel free to enter any questions you may have. I'm going to start things off. I want to start things off with Joe. So I'm going to ask Joe a question I'd like him to kind of go through with us, just to kind of kick things off. So Joe, could you please start us off by describing what direct georeferencing is and why it's important to UAV survey and mapping?
Oh, you gave me a tough one, Brett. I'm hoping most people have heard the term direct georeferencing before. It's something that Applanix is proud to have pioneered over the years, and one of the first companies to bring it to the UAV platforms. But as its name implies, what we're doing is we're directly geocoding the position in geographic space of a pixel or point collected from a mapping sensor on a UAV. And so the reason you want to do that is you don't need any ground information to do that, so it makes you more efficient. So traditionally with photogrammetry, if you didn't have a direct referencing system such as ours, you would have to go out, collect ground control points, and identify those in the imagery to do the georeferencing. With a direct georeferencing system that uses GNSS and Inertial, we're directly measuring the position orientation of every image or every laser scan so that we can directly put that position or point on the ground accurately in local mapping frames and projections. So that technology means you're a lot more efficient in collecting maps from UAVs. And so that's really kind of where we specialize. How do you map with a UAV the most efficiently at the lowest possible cost with the highest level of accuracy?
Great. Thanks, Joe. That kind of really sets the stage for this conversation. So as I say, if anyone has questions, please just enter it into the questions box. And I do have a question for Srdjan, maybe to just get him engaged in the conversation as well. So Srdjan, we've worked together for a while now, and you have a wealth of experience when it comes to turning your UAV into a professional mapping solution. What technology, hardware, software is required to support DG?
Well, it's basically GNSS receiver, a survey-grade GNSS receiver that is capable of tracking all constellations and frequencies. The antenna, applicable antenna as well, GNSS antenna, and of course IMU that is responsible for orientation. I would say properly calibrated IMU that inertial component that can deliver performance across entire temperature range. But one of the most important things is to understand your application. So exactly what are you trying to do? What is your mapping sensor? Do your air budget, and that will drive the requirements for proper GNSS inertial system. And of course, on the software side, post-processing side, that's GNSS, INS post-processing. Our product is PostPack UAV that can do augmentation with just about any corner case in survey that customer can face. So it is capable of doing with the single base processing without base station using PPRTX or smart base using the coarse network.
Okay, great, great. Joe, there's a variety of different methods out there for georeferencing, aerial triangulation, PPK. Direct georeferencing is the technology that we offer from Applanix, and direct georeferencing is starting to gain a little bit of traction in the market. We're seeing more and more people turning to direct georeferencing, but at the end of the day, not all direct georeferencing solutions are created equal. Just wanted you to kind of maybe dive a little bit deeper into why Applanix direct georeferencing. What are some of the things that we do that that make our direct georeferencing capabilities stand out?
So we're very much focused on understanding the application of direct georeferencing, whether it be on a UAV, an airplane, a ship, or a vehicle. And we understand the requirements each of those platforms or the challenges each one of those platforms brings to being able to produce maps efficiently. So what we do, for example, on a UAV, is we look at, okay, what kind of sensor is going to be on there in terms of a camera, hyperspectral scanner, and LiDAR. And we understand, what it takes to put, in the case of a LiDAR, that point at the right location on the ground as efficiently as possible. So we don't just understand GPS inertial, we understand how to apply that to put that point at the right location. And so what we will do, as Srdjan mentioned, we'll run air budget, we'll come up with the understanding of, in terms of the whole chain of errors, starting from the GNSS signal through to translating that position down to the inertial, and what the inertial errors need to be able to get that level of accuracy required to put that right location on the data. And then we use that to derive how we develop our products. So we are experts at inertial technology in terms of understanding what you can get out of these inertial sensors, whether it be MEMS sensors, ring laser gyros, fiber optic gyros, and also in terms of GNSS, because we're part of Trimble, we're intimately involved in everything to do with GNSS, from the tracking loops to the getting the low noise that you require. And so all that goes into our products, so that when we put a product out there and say, okay, for this application on a UAV on this type of LiDAR, we are going to guarantee that it works. And we're going to guarantee that you get that pixel at the right location or that point at the right location. So all of our systems are purpose-built. All of our IMUs are customized to our exacting standards to get what we need for the direct referencing on those applications.
Okay, great. Okay, so since I don't see any questions yet, I'm going to ask another question.
I do have some questions, Brad, sorry.
A few questions.
Oh, are there a few? Okay. Yeah, Cynthia, maybe you could just ask those questions, put them out there.
Sure thing. One attendee asked, is there any particular benefit for using dual IMU and or external IMU in UAVs?
I'll take that one. So yes, It depends, though. So our products support dual IMUs, and the reason we added that support is because in many cases, primarily on multi-rotors, you want to put your payload on a stabilized mount that's hanging below the drone. And a stabilized mount allows you to collect imagery or LiDAR perfectly level while the drone is moving around it. However, that presents a bit of a challenge because the sensors on the mount, but the GNSS antenna is on the airframe. So the airframe is effectively, and the antenna is moving around the sensor that's on the mount. So by having two IMUs, you can measure two sets of orientation. One, the orientation of the GPS is moving, and the other one, the stabilized mount, and that allows us to then precisely translate the position from the GNSS antenna phase center down to the sensing origin of the sensor. And so that's a huge benefit to having two IMUs when you're using these stabilized mounts. Now, and it's kind of unique to the UAV space because these small, simple mounts don't have extra information. On the big airborne systems like this, the big stabilized mounts, they already have what's called gimbal encoder data, so you can do this translation. But on the UAVs, a lot of those mounts don't have accurate output. So having the two IMUs allows you to easily and simply do direct referencing on a stabilized mount on a UAV. Of course, having dual IMUs also means you can measure, very precisely two sets of orientation if you have two sets of sensors that might not be rigidly attached to each other as well. So that's really the big benefit of having dual IMUs for UAVs.
Okay, thanks, Joe, and thanks for that question, Srdjan, who's actually a partner of ours in Turkey. Anyways, yeah, Cynthia, is there some more questions you could put forward?
Yeah. We have another question here. From the predicted practical point of view, when should the customer use AP14, AP20, or AP60? Do you have any real precision applied for each case, such as USB, helicopter, aircrafts?
So this looks like it's just, what are the differences between these particular board sets? Now, I noticed those are airborne, manned airborne products, or maybe you're referring to, no, well, there's kind of a mix there. So the products we have on the UAV side is the APX products. And Joe, did you want to take that one as well?
Yeah, I guess it doesn't really matter. I mean, we have different levels of performing products, whether it be for UAV, manned applications, or marine or land. And it fundamentally comes down to the accuracy, absolute accuracy, orientation accuracy that you can get out of the systems that you need to use to georeference your sensor. And that accuracy is driven by a couple of things: your dynamic environment. So if you're flying slowly or you're flying very fast, and you're flying height. So the higher you fly, the better your orientation accuracy needs to be to put the pixel or point at the right location on the ground. So as our numbers of, our product number goes up, the higher the orientation accuracy is needed, primarily because you're flying higher. So, with UAVs right now, most regulations around the world, you're restricted to flying height. So there, your absolute orientation accuracy is not as critical as when you're on a manned platform. That said, for low noise sensors, perfect example is like the Regal Minivox, you still need good relative orientation. This means sample to sample, so you need really quiet data to georeference those points sampled accurately enough. So there's sort of two aspects we look at. What is the absolute accuracy you need, and what is the relative accuracy we need? And that's how we design our systems, and that's how we guide which system should be used for which application.
Okay. Srdjan, maybe you could take this next question. It says, what is a good observation interval for the GNSS base station for processing the trajectory of a copter, say, for example, 6 meters per second with an APX 20?
Sorry, can you repeat for GNSS base station?
Yeah. What is a good observation interval for the GNSS base station?
Typically, the rate on GNSS base station it's not an issue. So it's anywhere 1 hertz to 5 hertz. It's just good enough for.
Yeah, I think is that implying data logging rate or base station separation? I think it means observation interval for the data collection rate. I don't know, maybe the person who asked that can clarify.
Data logging rate. They're saying it's the data logging rate they're interested in.
Okay.
For regarding base station separation, so what we typically say, it's like around up to 20 kilometers. So after that, atmosphere starts changing, and it's not
But
to use it.
When it comes to base station data rate, we use some pretty sophisticated interpolators. So even if you have, 1 hertz is plenty. Even if you have every 5 seconds, we can interpolate. But we typically recommend 1 hertz is all you need.
Okay. Santhia, could you help us out with another question? Do you see one there?
We have a question here, focusing more on like bigger ideas. So we have a question saying, Applanix has always led the way in positioning technology. What do you see as the next big development in the UAS positioning market, or have we hit the wall?
Who asked that one?
Tim Peterson.
That's a loaded question.
I think everyone taking this.
We have not hit the wall, my friend. The next big thing in terms of positioning, of course, is using your sensors to aid in the positioning. In other words, what you commonly hear is visual odometry or SLAM or map-based localization. So that's basically an extension of what we call multi-sensor fusion. So our products actually are not just GNSS fused with inertial, we fuse with all kinds of different sensors, DMI, precision fixes, etc. And in our autonomy products, if you've ever been on our website, you'll notice that we talk about SLAM technology and map-based localization and visual odometry. So when it comes to UAV, that's kind of the next, pulling that technology into UAV positioning is kind of the next step. The question is, what are the benefits of that? So if you're flying a UAV in between buildings, or you're flying map tunnels, etc., that's where that technology comes into play. If you're open sky, GNSS is getting so accurate with all the constellations, all the observables up there. As we're proving with our PPRTX, you can get that centimeter accuracy pretty much anywhere as long as you have open sky. So it's really going to come down to the value bringing these other positioning technologies into the UAV space, but it's definitely going to come. Where you can see the obvious thing is if you're trying to do not necessarily mapping projects, but also cargo delivery where you need precision landing, 100% redundancy if you get GNSS jamming, that sort of thing.
Okay. Thanks, Joe. Lars has a question here. He says, I have a question regarding PPRTX and Applanix smart-based post-processing systems. Where does the correction data in both cases exactly come from, and how can centimeter precision be achieved? Maybe you want to take that one, Srdjan. So it looks like a question around PPRTX and how that works, and smart-based how that works, where those data corrections come from.
Well, this is two different technologies. So basically, let me start with the smart base. So smart base is the network of the core stations that are available out there. So basically, what in post processing we do, we connect to the network and download the all local base stations. So, and based on the base station data, we do virtual reference station basically that travels with a rover. So baseline is 0. So of course It depends on the geometry of the smart base. It depends, the quality depends on the available GNSS receivers, GPS receivers, and so on. And one disadvantage of the smart base, it's availability. So it's basically you need to wait 24 hours to grab those data. PPRTX is basically completely different technology. It's run by Trimble based on the global network of the base stations, where the corrections for particular location for whole Earth basically are stored on the Trimble server. So what PostPack does, it's basically goes to the server. It's available immediately after the mission. It goes to the server and grabs the corrections for particular location of the survey and basically applies them in the post-processing workflow.
Excellent. Excellent. Okay. There's another question here from Srdjan. Can you please go over upgrade options between the APX boards and also the AP boards? Srdjan, do you want to try to take that one as well?
Sorry,
Yeah, can you please go over upgrade options between the APX boards and the AP boards? So I guess this would be.
There is maybe the question is needs to be reframed. So APX boards typically we use for the UAV market. So it starts on low end, and they're designed to fly up to FAA limits for certain sensors. So while AP boards are basically go all the way to AP60 performance for man-operated system. So they are designed for typically to address the big, huge sensors on man-operated systems. So there is really, if you choose right your sensor for your application, your GNSS INS, there is really no need for upgrade from APX to AP because it's completely different.
But I think maybe the question is, we have a new AP Plus product.
Yeah, so I was going to ask that.
AP boards, maybe that's the question.
Yeah.
Because the AP Plus is our next generation product. So Srdjan, maybe that's clarify.
Yeah. Yes, so the AP Plus is our next generation product that we released back last year. So the advantage of AP Plus is size, weight, and power. It is extremely small, that can be used in UAV applications and in main applications as well. So it starts on very low end as a AP Plus 18. And goes all the way to AP Plus 60. So upgrade from one to another product is basically the external IMUs that provides the orientation quality for the mapping application.
Okay, so the APX boards for the UAVs, the AP boards for the manned airborne, and the AP Plus, you could use it, I guess, basically if you're looking at kind of moving a sensor payload from a manned to an unmanned vehicle.
The way to look at it is AP Plus is a replacement for AP, but it's got a much broader usage case because it's got a smaller size, weight, and power, and because it has dual use support for IMUs. So that's why we consider it our next generation platform. It can be, considered even dual use. You could put a payload together that will be small, light enough for UAV, and then move it to a manned platform, that sort of thing. So it's a much more versatile product than the AP, and that's why we've launched it.
Okay, great. So we've got kind of all the areas covered there. Cynthia, any more questions coming in?
Yep, we have one here that says, For instance, can AP20 be used instead of AP60 in a LiDAR system mounted in a helicopter? Yeah, again, this is a manned application.
The answer is yes, but it depends on your flying height and then the type of LiDAR. So a lot of the helicopter-based LiDAR systems are flying low. So the air budget is such that you can use an AP20 depending upon the swath width. So again, this comes down to understanding what your air budget is on the ground. So what accuracy you need on the points and the pixels on the ground, and then kind of what your sensor geometry is, and that backs into what kind of accuracy you need on the direct geofencing. So that's the kind of thing that we can help, but also our OEM partners are very versed in what they need in terms of supplying a georeferencing solution for their sensors.
Okay, Joe, there's another question here from Ryan. He says, has anyone used an Applanix product for navigating flying cars?
Are there flying cars?
Well, I guess there's a whole bunch of unmanned
I guess that refers to the new urban air mobility products that are coming out.
Yes. Yeah.
I can't comment on that, but I don't really know, to be honest. I know, our products are used all over the world, but no comment.
Yeah. I think you're right, Joe. The urban air mobility is an emerging industry within the UAV industry. A lot of exciting things happening there, but there's still a lot of developments, before we get to the point where some technology is going to be deployed for that. I know that I've talked to at least one customer on this who's looking at around 2025 having some sort of demo capability. But yeah, that's still a lot more to come on that for sure. Okay, Cynthia, any other questions you see there?
Not currently.
Okay. So if you have questions, just enter them into the questions box, and we'll get them answered here. I've got one here for Srdjan, one that I actually get asked quite a bit, and it's basically involves the integration of our direct georeferencing technology with a variety of UAV platforms and sensor payloads. Srdjan, could you please just take a moment and describe what is typically involved with integrating this technology in a UAV platform? A lot of people wonder, what it takes to go from the components such as the integrated GNSS IMU board and the antenna, getting that integrated, what's involved in all of that, and kind of what experience do you need to kind of complete that if you're going to complete that on your own?
Yes. Well, I always say building survey-grade payloads, it's not a rocket science, but it does require passion, so engineering passion. There are 3 stages that you go during development up to final product. So it always starts with the right mechanical integration. So mechanical integration, I would say, okay, mounting the antenna properly in the way to minimize the cycle slip to get that extra positioning accuracy from entire GNSS constellation. So the second thing is proper mounting of the IMU or inertial unit has to be hard mounted to the mapping sensor itself. And on the mechanical, the third way is proper vibration isolation of the payload itself. So you want your inertial component to sense the true motion of the mapping payload and not the motion of or interferences vibration of the vehicle itself. So the second thing is proper electrical and real-time integration. You want to do the proper time synchronization to time tag all your raw sensor measurements with a GPS time accurately down to microsecond level. And the third way is, of course, payload calibration. So payload calibration, definitely depends on your mapping sensor. So if it's LiDAR, how you can calibrate the laser, each LiDAR laser. If it's camera, how you calibrate the lenses, focal length, principal point offset. Do you do inner calibration? Do you do terrestrial calibration? And one of the important things in payload calibration with respect to IMU is it's to calibrate the bore size. So when you do hard mount of the IMU to the mapping sensor, so the mounting angles are always residuals, and those residuals needs to be calibrated through the post-processing software, and basically they would be stable as long as the payload is intact and the IMU remains hard mounted to the sensor itself.
Yeah, so so you need some engineering experience to be able to do that, but I know at the same time we we have configuration guides and integration guides that kind of help along the way, and we've worked with many different types of sensors in the past and currently as well, just all kinds. So in fact, that kind of leads me into another question here for Joe. Joe, we're seeing a lot of, and this is a question I get a lot, is that people are looking to use LiDAR, and LiDAR is very commonly used in survey and mapping, and not all LiDARs are created equal, of course, but why is DG so important to properly getting point clouds geo-referenced when you're using LiDAR?
Well, most LiDARs, other than flash LiDAR, is it's a scanner. So you're continuously scanning back and forth or scanning in a circle while the aircraft, so the UAV, is moving. So you don't have this, like a photo, which is taking a snapshot of all these pixels together. You don't have that, what's called image. You just have a single point, and then by the time it can, measure the next point, the aircraft's moved. So it's really, really difficult to take out, aircraft motion from these points unless you have position orientation of the aircraft. Unlike photogrammetry, where you can use a process like AT, with LiDAR, it's very difficult. You can do it, but it's very intensive and very expensive. So that's why with direct referencing, we kind of say, well, with cameras, you should be using it if you want the maximum productivity and lowest cost. For LiDAR and other scanners like hyperspectral, you really need to use it if you want any type of accuracy. And that's just the fundamental difference in the types of the scanners, types of the geometry of the sensors.
Okay. Cynthia, do you see any further questions we have today?
Yeah. So we have a few questions that are connected. So what are some factors that can affect the bore sight calibration? Should bore sights be recalibrated after certain periods of time? And also, can we get higher lever definition on the difference between bore sight and lever arms? So
Srdjan, maybe you might want to take that one. That kind of continues on from your previous answer.
Yeah, pending, we do have bore sights procedure depending on different mapping sensors. So typically the accurate bore sight calibration requires flying certain calibration pattern. So it's in case of camera with and you do in case of camera, and when you do bore sight together with inner camera calibration, we always request to fly two different heights and opposing lines and cross lines as well. With the LiDAR, it's similar as well. We would like to have the cross section with rich features on the ground. So that's basically the limiting factor, scenery on the ground. So the bore sights should remain stable remain stable as long as the payload is intact, and the IMU remains hard mounted to the sensor itself. Of course, we always recommend to check bore sites once in a while, so after extensive use due to vibration and so on. So just to check it and to do the recalibration.
Okay, great. And there's another question here from Lars. It says, Srdjan was talking about positioning the antenna. How large would you expect the impact of obstacles, such as a few centimeters of styrofoam covering the antenna, on the possibility of achievable accuracy? Srdjan, maybe you want to take that one as well. That's more about positioning the antenna to get the best results.
There are two issues with finding and positioning the antenna. The first is emission from the platform itself. So that due to emission, it can cause the cycle slip issues on particular frequencies. So the bigger the distance is from the platform itself, so you basically minimize the cost of that. So we always recommend to position antenna at the highest point, above the rotors, for example, on quadcopters, and of course it has to face the open sky. So any obstacle around, so it can produce the cycle slips. So that is basically, that would produce the best scenario for antenna mounting the antenna. And in addition to that, we always recommend to ground antenna properly. So if you put the metal disc or plate underneath antenna, so to ensure that grounding is done well.
I guess in terms of covering, the question about covering an antenna, we do not
covering the antenna. So the antenna elements the antennas that we supply are already covered. So we use the helical technology. The elements are already covered inside the antenna. So if you want to cover that antenna, so it's probably not a good idea to get performance out.
Yeah, I guess in some airframes, such as fixed wing, there's a concern about aerodynamics, and we do have patch antennas that, again, covering them. You have to be very, very careful about covering an antenna, making sure that the signal is not attenuated anyway. So it can be done, but that's one of these things you have to be very, very careful with.
There are patch antennas. There are patch antennas available, survey grade patch antennas. So that is basically completely different integration process on patch antennas.
Yeah, I guess we have two options, right? We have the helical options, which are really high performance, and then we have the flat antenna, right? The disc antenna. Get it out of the slipstream.
Okay. We have another question here from John. He writes, when integrating a new UAV, how accurately should the rover antenna be measured to the IMU? Down to the millimeter, or do you have any kind of guidance there?
Well, there's sort of two sets of measurements that you have to do. One is from the origin of the sensing center, right? So the origin of your LiDAR or camera to the IMU, and then from the origin of your camera to the GNSS antenna. I think I saw a question about the definition of lever arms versus bore sights. So what a lever arm is the vector, the physical distance from the origin of your sensor to the GNSS antenna phase center, and from the origin of your sensor to the IMU. Those are what we call the lever arms, because they're effectively little levers. And those need to be measured so that we can translate the position both from the GNSS to the sensor and the IMU to the sensor. Now, In terms of accuracy, the better the accuracy on those lever arms, the better you can translate the position. And we use the entered values plus the orientation we're computing to translate the position. So in terms of the lever arm to the IMU, usually that's closely mounted, and you can get that from a drawing, and you want to get that down to, you know, less than a centimeter, a millimeter is ideal. To the GNSS, it's a lot trickier, right? Because there's a face center and it might be above you. But in general, if you're trying to measure the position of the sensor origin to the, you know, 1 centimeter or better, which you can get from GNSS, your lever arms have to be measured to better than a centimeter. So we typically say, you know, you want to try and get them down to half a centimeter on a UAV if you can. Then you don't have to worry about them adding to any error you're going to get from the GNSS. It's on a UAV, it's actually quite easier to do. On an airplane, it's much more challenging, and some people actually use the total station to measure in the GNSS antenna. But again, if you're after that, you know, centimeter level GNSS accuracy, then you need to make sure your lever arms are measured better than that. And it's the same with your bore sights. The bore sights are the physical misalignment of the IMU with respect to the sensor. So you need to know that the IMU is misaligned with that sensor so you can compute the correct orientation of the sensor. And that's where bore sighting becomes critical, because if you don't do that, you're adding orientation errors to your output. And that's why we offer tools such as LiDAR QC tools to do the bore sighting for LiDAR, and photogrammetry tools to do the bore sighting for cameras. There we're actually using, you know, traditional photogrammetric techniques for the camera calibration, and we're using a global SLAM least squares adjustment to determine the bore sights from the LiDAR data. So those are very robust, accurate methods of bore sighting.
Oh, thanks, Joe. There's another question here from Christian. He says, in my case, the antenna model of our base station, TopCon HR, is not included in the drop-down menu of POSPAC. Is it causing problems in the processing if I use the unknown model? That's a POSPAC question. Maybe that's a question.
Buy Trimble. You just gotta throw out that TopCon, buy Trimble, you're all set.
Yeah, that's right. Yeah, you won't have any problems.
That's a loaded question, Srdjan.
Yeah.
Yeah, it's always the challenge to support in database to support just about any. I'm sure we support plenty of TopCon base stations antenna as well. So just the problem is like, okay, whenever they release something new or something like this, it really takes time and to get it in database. So using undefined antenna or unknown antenna, so it's not optimum scenario as well. So it's always better to have the model itself. So it might have some performance issue, and most of that would be probably constant bias in
without the model, we're not able to put the phase centers where they need to be. So we have to make an assumption, and your antenna has different phase center offsets. And so when we don't have the model and the receiver has its own biases, we don't have those models, then we're guessing. But as the Srdjan said, the net effect might be a bias in your output, typically vertical bias. You know, a centimeter, a couple centimeters. Okay. For LiDAR, that might be a problem. But again, you know, it's one of the challenges is working with all these different base stations.
So Joe has a kind of a follow-on question here. He says, final question from me, where will you see cycloslips when looking at the raw trajectory data? Will it just be degraded accuracy, or will you see flight line drifts?
That's another loaded question. So where I mean, our first rule of thumb is always check your raw data, right? So in POSPAC, you can display your raw GNSS measurements. You can display the signal noise ratios. You can also display plots that show cycle slips, detected cycle slips. So there, you know, if you've got a problem with jamming, or you've got a noisy installation, or you've got a loose cable, you'll see lots of little black crosses, lots and lots of cycle slips. When you're doing a turn or something, it's normal to have the odd cycle slip. But if lots of these cycle slips, okay, you've got some problematic data. Then the next step is, well, what we do is we run a GNSS QC step. So we say, okay, let's just see what that data, those raw observables coming from the rover matched with base station on the ground. Let's run that QC step and see if we can see how good that GPS data is on its own without adding inertial in the mix. And there we say, look at your forward reverse separation plot. If your forward reverse separation plot is basically consistent, you know, you might have some cases where it jumps up and down if there's a cycle slip, but if it's consistently, you know, matching at the centimeter level, a couple centimeter levels, few centimeters level, then you know you got good GNSS data. If you do see some jumps in this forward reverse separation where you have cycle slips, that's okay, because then the next step is the inertial fixes it. So once you run it with inertial tends to fix all these issues. The challenge is how well it fixes those issues. So we've tried to tune our processing so that you know, when you get that RMS value coming out for position, it kind of, we're trying to include any effects of cycle slips. So really though, you know, the first rule of thumb is look at that raw data, look at the GNSS only solution, and from there you kind of know you're okay going into the next inertial step. Like if you get 100% fixed on your QC step, you're laughing, right? And if you don't, if you have a few cycle slips, the inertial can fix to that. It's really when you have problematic data, like a bad antenna, bad connection, that really comes out in the QC step.
Okay.
Hope that answers the question.
Yeah, I think that was pretty good. Joe Srdjan, there's another question here. For an aircraft installation, on the reference to GNSS antenna lever arm, can the POSPAC calibration processing is accurate enough to derive the accurate lever arms this way? Not sure I get that question. Maybe you.
That's another loaded question. I like these questions.
So, yeah, I'm not sure who best to direct that one to.
So the lever, as I mentioned, there's two lever arms. One is from the sensor origin to the IMU origin. The other one's from the sensor origin to the GPS antenna. The lever arm from the sensor origin to the GNSS antenna is observable in the processing in the column filter, but the lever arm from the origin to the IMU is not. So you need to get that measured correctly. You cannot observe that independently in the column filter. The other lever arm is observable, but primarily in horizontal only. So the issue is that when you're flying, you're not doing a lot of up and down, right? You're not doing a lot of this. So it's that type of motion that makes the vertical lever arm observable. You're not doing that in an airplane. Horizontally, you're doing all these turns. It's very, very, very observable. So what we do is we say, okay, you can use the estimates to check your lever arms. Horizontally, you can say, okay, I can calibrate them. Vertically, you can check them. So if you're totally wrong vertically, you'll see that it's coming up with a completely wrong value. I got to go back and check and measure it. But once you've checked your lever arms, and by estimating approximately correct values, if you should be able to get estimates to a few centimeters accuracy, then you turn them off and don't let the column filter estimate them, because there is this uncertainty in the vertical that you can't get perfect vertical lever arm estimation. But it's a good quality control check.
Okay, great.
I guess it depends on the quality of IMU itself as well.
Yeah, and the dynamics and the speeds of the turns, stuff like that.
Yeah, always lots involved. Cynthia, do you see any other questions here?
I think we've asked all the questions we've had so far.
Great. Okay, so what we'll do here is we've got about 10 minutes left. I just wanted to, if you do have any other questions, you can type them in now. I just do want to reiterate a little bit about some of the things we have coming up that you might be interested in. Tomorrow morning at 10:30, we have a session on it's learning all about direct georeferencing for UAV survey and mapping. This is a Spanish session only. We've never done a session in Spanish, but I just want to kind of put a plug in for any Spanish speakers that would prefer to operate in that language. We do have a special session tomorrow for that. And then in the afternoon at 1:30, we're going to be talking about GNSS augmentation solutions and how they work and what options are available and what correction solution you might want to use in a certain situation. So we'll be addressing that tomorrow at 1:30, and then on Thursday, on May 6th, we have a session on POSPAC. It'll be how does POSPAC work, a little bit about POSPAC training, what you can do, and how POSPAC works with our products. So if you're interested in any of those sessions, please feel free to sign up. You can sign up on our website. If you go to our website, it pops up right away, and you can just sign up for any of these sessions like you did for this one today. And on that note, if there's no more questions, we'll just kind of close it there. Any concluding comments, Srdjan or Joe, before we go?
Thanks for the great questions. I actually really enjoyed this, not being able to go out of my house to actually interact with people. This is quite refreshing, to be honest. I really miss going to the conferences in person and having the chat. So I found this quite refreshing, and thanks for all your good questions.
Great.
Yeah, thank you from my side as well. So I can just reiterate, I wish we are in conference and talking in person about resolving those issues and so on, but it's gonna happen sooner or later. So.
And having a cold beer while we do it.
Sounds great. Yeah, looking forward to that. Anyways, everyone's saying, or I'm getting some thank yous here, Joe, Srdjan. So really thank you for your time and taking some time out of your schedule to be with us. I think this was very helpful. As you say, Joe, there was some great questions that were asked today, and happy that we could have a chance to answer those. So hopefully we'll see you in some of our other sessions, but right now we'll wrap it up, and we'll again thank you, and we'll say goodbye. Thanks everyone.
Bye-bye.
Thank you.